Functions and expressions. A mathematical function consists of input parameters and a return value. The return value is uniquely determined by the values for the input parameters. Stated differently, there can only be one possible return value for a given input. A function in the context of a programming language is embedded in an execution environment. This includes memory, disk drives, network connections, and more. For example, a function could request the answer for a given input from a server. But this could violate the unambiguity requirement because the server might change the answer to the same input at some point. So this would not be a function in the mathematical sense. It is also possible that during the execution of a function, the environment is modified. This is called a side effect. If the execution of a function does not require interaction with the execution environment, then it is called pure. The advantage of pure functions in programming is that their behavior is easier to test. For example, suppose you want to write a function which changes the contents of a database based on some input. For every test of the function, you would need to reset the state of the database. To solve this, you could split the function into two parts. A pure one, which returns the database command which describes the modification, and a second function which executes this command. Functions can be described in different ways. One way is to describe them using natural language. In this case, f of n is the largest prime number that comes before n or n itself. Let the function c denote the pairing function, which assigns a unique integer to every pair of numbers. The right picture describes a method to compute it. For example, c of 1, 1 is 4 because you must go from the origin one step right to 1, 0, then to 0, 1, then to 2, 0, and after the fourth step, 1, 1 is reached. An alternative way to define this function is this expression. Don't worry if you don't see why they both define the same function, since it is not obvious. What is important here is that expressions provide a simple and unambiguous way to describe functions, unlike a natural language description or a definition by example, which require human interpretation. In functional programming languages, every function is defined in terms of an expression. We will use trees as default representation for expressions. An expression is a tree labeled with variables or input parameters, as we called them before, and functions. The green nodes are variables and the rest are functions. Constants can be seen as function without input. So in the right example, 1 and 2 are constants. Basis functions are a set of functions that may be used in an expression. This term is analogous to the term basis vectors in linear algebra. Consider the top set of definitions. Assume that addition, multiplication, 1 and 2 are the basis functions. The call graph of such a set of definitions is defined as follows. First, add a vertex for each function. And then, if the defining expression of a function contains another one, then add an edge. So in this case, since the defining expression for f contains g and h, we draw an edge from f to g and from f to h. And since g's expression contains h, we draw an edge from g to h. We say an expression is recursive if the function it defines leads to a cycle in the call graph. For example, all the expressions in this example are non-recursive since the call graph is acyclic. But if we change the definition of h, then the graph gets another edge. And now the expression for f is recursive because it leads to the cycle gh. And the expressions for g and h are recursive as well because they are already part of the cycle gh. Assume the call graph looks like this. Then the expression for p must be recursive because it also leads to gh. And the expression for q is non-recursive because it doesn't lead to any cycle. Usually, in the context of programming, people say a function is recursive to indicate that its defining expression is recursive. Strictly speaking, this is not a property of a function itself, but the expression used to define it. Therefore, we prefer to say recursive expression here. Also, it is good to know that the term recursive is used in theoretical computer science as synonym for computable, which indeed is a property of a function. Let us try to come up with an expression for addition. In this example, we may use the shown basis functions. The function if is defined such that if the first argument is true, then the second argument is returned, otherwise the third. In the example on the right, it would return y plus 1 if x equals 0 and y minus 1 otherwise. The idea for the expression for add is to add 1 y times to x. Due to the limitation of our basis functions, this requires the use of a recursive expression. If y equals 0, then we know x does not change. This can be expressed as shown above. And if y is not 0, then we use the second equation. This can be added to the expression at the third child of the root. In this case, the call graph consists of only the node add, which has a self loop, and thus its expression is recursive. As practice task, try to generalize this example to integers. This requires the additional function less than 0, which returns true if and only if the input is negative. Different programming languages use different ways to represent expressions. We start with a tree representation and show how it can be converted to prefix notation, and then to the common mathematical notation. To convert this tree into prefix notation, we proceed as follows. Look at the root node f. First, we add a pair of parentheses for it, and then we look at the first child of f, which is x. And again, we add a pair of parentheses for it, which now must be placed inside the first pair. And then we go to the next child, g, and do the same. And we repeat this for the children of g. So with y, then with z, and finally with w. Notice that each left parenthesis corresponds to exactly one node in the tree. Now we just have to write the corresponding label after its left parenthesis. And then we remove the parentheses around leaf nodes. And now we have the expression in prefix notation. This is a notation used in many functional programming languages. Next, we consider how to go from here to the mathematical notation. First, we copy the prefix version. Then we swap the labels with their left parentheses. And we add commas between the children. And finally, we remove the spaces. This is probably the most widespread notation used for expressions in programming languages nowadays. In infix notation, a function with two input parameters is written between its two arguments. If a function is associative, then one can omit parentheses in this notation because they don't affect the result. So stated differently, the order of evaluation does not matter for this expression. A function is called left associative if leaving out parentheses means that the leftmost pair is evaluated first. Similarly, it is right associative if the rightmost pair is evaluated first. Since addition is associative, the choice does not matter in this case, because it will always yield the same result. But if we choose a non-associative function, such as subtraction, then choosing between left and right associativity makes a difference. If two different functions are used in infix notation without parentheses, then it needs to be defined which one comes first. This is called precedence. If we say addition has higher precedence, then this would be interpreted as 2 plus 3 and then times 4. And if we say multiplication has higher precedence, which is the usual convention, then we multiply first. And we would say multiplication has precedence over addition. In imperative programming languages, one usually uses sequences of assignments. Let us see how such a sequence can be converted into a single expression. We use this sequence of assignments as example, and we add line numbers to refer to them. For the first assignment, we can just copy the expression. For the second assignment, we do essentially the same. Now notice that we wrote a with index 1 to refer to the value a had after executing line 1. And now we can insert the expression associated with a1. For the last assignment, we do the same. Write down the expression in that line and insert the expressions for a from line 2 and b from line 3. Thinking in terms of sequences of assignments can be seen as building an expression from the bottom up. People who are used to imperative programming languages might feel more comfortable with the bottom-up approach than trying to construct large expressions top-down. If you struggle to write a big expression, try to write a sequence of assignments which express your intent and then convert them into an expression as shown here. This concludes the video on the basics of functions and expressions. Thank you for watching.